Amy introduce you, or Cindy introduce you, Amy.
Hey there, just so everyone knows that we are recording this session, and I think the little auto voice just went off, letting everyone know. But I guess we'll get started. Hi, everyone. It's my pleasure to introduce Dr. Amy Williams, a University of Florida Assistant Professor of Geology, as well as a NASA Curiosity rover mission collaborator and NASA Perseverance rover mission participating scientist. Amy completed her master's in Earth and Planetary Sciences at the University of New Mexico, her PhD in geology at UC Davis, and was a postdoctoral research associate at NASA Goddard Space Flight Center. With her research centering around terrestrial planetary analogs and biosignature detection, Amy has received several group awards at NASA for her work on the Curiosity mission, a nomination for the 2017 Maryland Academy of Sciences Outstanding Young Scientist Award, and a nomination for Faculty Mentor of the Year Award. Amy is beyond talented in fostering scientific curiosity and professional and personal growth in her students, and is always eager to support their development. I am very fortunate to have been taken on and mentored by Amy in my undergrad at UF, and I'm eager to see what exciting happenings she has to talk to us about today. So Amy, I'll leave it to you. Thanks for coming.
It's incredibly kind, Sydney. Thank you so much. Thank you for that lovely introduction. And thank you all so much for joining today. I'm so excited to speak with you about my Mars research, about what's going on in our terrestrial analog research. And, you know, I've got a couple of slides from the last couple of days of rover operations with Perseverance. So we can go ahead and get started. And I'll tell you, I try to make at least part of this presentation interactive, even though we're all online. So I know we're all going to turn off our videos, but if you're willing to interact and turn on your video for a minute and or turn on your chat, what we're going to do is have a little conversation here that may be most specific for the geology oriented folks. So let's see what you think about some of these images. So I'll just start out by saying this is a 1 planet, 2 planets, red planet, blue planet. It's comparisons of biosignatures on Earth in our search for biosignatures on Mars. So here we go. So I'm sharing with you an image from the Curiosity rover. This is from the Vera Rubin Ridge campaign from a couple of years ago. And so this is an outcrop on Mars. And so if you take a look around, especially the SED-oriented folks around here, your eye may be drawn to a couple of regions, maybe this upper right-hand corner. So let's zoom in on that a little bit here. Okay, so here is this strange looking texture in these rocks at Vera Rubin Ridge. Let's zoom in a bit more. This might be a kind of compelling rock. So the question I'm posing is, did we just find life on Mars? So what I'd like to ask folks to participate in is, especially those who have experience with SED, biosignatures, sedimentology, and stratigraphy, what does this look like? So you can respond verbally, you can respond in the chat. I'd love to hear from folks. What do you think these textures look like? Trace fossils from multiple people. Ooh, tool marks, all right. Or burrows, right? Tool marks can be abiotic potentially. I don't know if what else could be scratching along the surface, but yep, absolutely. Freeze thaw, I like it. Ooh, feeding traces, excellent, excellent. All right, fabulous. Yes, so this is, ooh, flute casts, very nice. This is the diversity of responses I often see, mud cracks, fantastic. So here we go. Okay, so this is the next day. It's a new angle. We've kind of bumped the rover over and we have better and different lighting. So now we are looking at that image again. So did we discover a paradigm-changing Martian biosignature or just differential erosion of a float rock in an area that we know has extensive diagenetic alteration? So in this case, it happens to be the latter. So thank you for participating. I really enjoy kind of getting people's attention with this, because when we saw this, when these images came down a couple of years ago, we had to stop and say, is it is it possible? Is it possible that you're seeing burrows, that we're seeing feeding tracks, that we're seeing something like that? And that's the question that we always have to ask ourselves, is to not get complacent, to always assume a priori that there's an abiotic reason, but then to make sure that we are looking in depth at this stage, hundreds of thousands of images that we've acquired from the surface of Mars with our rover operations. And so I think this does a really good job of illustrating the challenge of geobiology. That challenge is to identify a feature as demonstrably biogenic or abiotic. And I've got an example here of these gorgeous Cambrian stromatolites from outside Saratoga Springs in New York. Stromatolites sort of being the poster child for the challenge of biotic versus abiotic formation. And so we're going to take that broad concept and apply it to the search for biosignatures beyond Earth. So my research program is sort of wide ranging, but it generally focuses on the processes that preserve evidence of microbial life. So that's what we call biosignatures, evidence of that life, even if it's gone now. And methods to detect those biosignatures in both the terrestrial and the Martian rock record. And so we're going to have a mission arc here going from the Curiosity mission over to our most recent NASA rover mission, Perseverance. So part one here is going to talk about the search for organic matter on Mars in Gale Crater with the Curiosity rover, and specifically the SAM instrument. And then part two is going to talk about the search for biosignatures and the plan to return samples from Mars for the first time from Jezero Crater with the Perseverance rover. And so let's jump into the Curiosity rover side of things. And I may not be able to keep track of chat here. So if you want to ask questions in the middle, feel free to interrupt me. If you want to wait till the end, sounds great to me, whatever you'd like to do. Okay, so let me just orient you to the variety of missions that NASA has sent to Mars. We've got Viking 1 and 2 is sort of our starting point for the search for life, biosignatures, and really in situ exploration of the red planet. We've had, of course, several landers and rovers since then. The second most recent rover mission is Curiosity. Curiosity is still operating after almost 9 Earth years, so about 4 Martian years. Now, we've been exploring Gale Crater for this entire duration of the mission. We've identified habitable environments that contain evidence for ancient water, minerals in both the oxidized and the reduced forms, and organic carbon. So this is everything that terrestrial microbial life needs to survive. We've also identified ancient lake systems in Gale Crater that were sustained for on the order of tens of thousands of years. And so we have this highly habitable environment in the past. And the question remains, was there ever life on Mars? So here's the toolkit that we use to try to address this question. There's a series of different kinds of biosignature categories that we can use to try to answer the question of whether something is made by life or not. So these start out with the presence of select minerals. You can have these micro scale textures, isotopic analyses like Tom was just describing, chemistry, macro scale structures, and the presence of diagnostic organic carbon molecules. So all life on Earth as we know it is made up of organic carbon. And so this is one of the motivations for using that as a biosignature tool. So that's what we'll end up focusing on a bit more in this talk than the morphology side of things. Although the search for morphologically distinct biosignatures like those gorgeous stromatolites are something that we always keep our eyes out for when we're looking at the outcrops on Mars. So let's talk about the Curiosity rover and let's talk about the instrument that can detect organic carbon. The SAM instrument, which tells you actually nothing about what it does. SAM stands for Sample Analysis at Mars. It is actually a suite of instruments capable of detecting organic carbon. This is the first time that we've really sent such a capable instrument suite to Mars. So this instrument contains, so we'll get into the specifics here for those who do this kind of work, 2 pyrolysis ovens, or ovens you can heat up to about 1,000 degrees C, 6 different gas chromatography columns that you can see in the bottom right here, a quadrupole mass spectrometer to detect those molecules, and even a tunable laser spectrometer to detect the isotopic signatures in certain gases like methane. So among all of these capabilities, SAM can detect organic carbon with this process we call pyrolysis, gas chromatography, mass spectrometry, or pyrolysis GCMS. So this is kind of the core technique that my lab's been using for the past few years to compare our results with what we can do on Mars. We do these experiments both with and without these specific chemicals or reagents that make these organics more detectable or amenable to the GCMS analysis. And so what I want to do is show you the most simplified version of how the SAM instrument works so you kind of understand where our data are coming from here. So on the top left here, this is actually the sample carousel inside of SAM. And this is able to hold 74 sample cups that we can deliver powdered drilled Martian bedrock to for these analyses. So in each one of these cups, you can see all these nice clean white quartz cups, and there's a couple of metal cups as well that contain these chemicals that we can perform these specialized experiments with. So let me show you just the most basic flow diagram of what happens inside of SAM. So the very first thing we do when we collect a sample, we put the sample in the cup, and then we heat the cup up inside of that pyrolysis oven up to almost 1,000 degrees C, which is going to break down every mineral almost that we can expect to see in Gale Crater. And so what it's going to do is it's going to heat up the sample in the cup here, and we're going to send it straight to our mass spectrometer to identify these volatile gases that come right off of the sample. So EGA is the term that we use to describe this, evolved gas analysis, and you'll see this acronym a few more times in the talk, but it gives us this bulk chemical detection versus the temperature at which it evolves from the sample. It allows us to understand the temperature at which organic carbon is evolving from the sample and helps us focus our GC analyses in the next step here. So in step 2, this is when we use our chromatographic columns. So these are basically extremely thin tubes. In this case, they're 60 meters long, and they're about a quarter of a millimeter in diameter. They're tiny, tiny, tiny. And so what we're doing is heating up the sample, and instead of sending it straight to the mass spectrometer, you trap all of those organics onto our hydrocarbon trap here, shown in green for no better reason than it's a nice color. And then the organic carbon is sent to one or more of our gas chromatograph columns, where the molecules in there are separated out based on their mass. And so from there, they're able to be sent to the mass spectrometer for detection, and we can tell exactly which organic molecule we're looking at. Now, I told you there are a couple of chemicals and reagents we can use to perform these specialized experiments, and that's what step 3 is here. So we actually carry 2 different chemicals to perform these experiments. One is called, are you ready for this? MTBS-TFA. You have to practice it a lot to be able to say it like that. And so it's able to perform a certain kind of reaction to make these molecules more detectable. The other alternative on the mission is TMAH. And so I'm going to define these acronyms for you in just a second, but just know that these are 2 chemicals that kind of get at the same final goal of making these organics detectable, but they do it in different ways. So let's talk about that just for a minute here. So sampled organics are going to be made volatile and therefore detectable to this technique using either that MTBS-TFA derivatization, and here's the reaction down here. The key to take away here is the molecule we're reacting with here is adding this big, what we call a silyl group onto, for example, an amino acid of interest. And so this is going to make that amino acid detectable to the GC. But you can imagine silicon and all of these carbons, that's a really big molecule. So there are other challenges that come with using that particular chemical. So what we can also do is what we call TMAH thermochemolysis. So TMAH stands for tetramethylammonium hydroxide. This chemical just adds this cute little methyl group, a carbon and 3 hydrogens, onto the molecule of interest. In this case, this is a carboxylic acid that I'm showing you here. And I'll show you why these are important in just one moment, but you can imagine that this is going to make a much smaller volatile molecule that can more readily pass through those really, really tiny GC columns. And so this process of thermochemolysis, this is just degradation of organic compounds, kind of breaking off this hydrogen right here and adding this methyl group through heating them in the pyrolysis oven in the presence of that reagent, TMAH or MTBS-TFA. And so, as I've said before, we only have a couple of these chemistry experiments basically on board the SAM instrument. So there are 9 wet chemistry cups. Of those, 7 contain MTBS-TFA, and then only 2 contain TMAH. And so what we do, these are one-time use experiments. What we do when we're ready to perform this experiment is, you can see this foil cap at the top image here. We puncture the cap, we deliver the solid sample to a tube containing that reagent, and the reaction is ready to begin once we put this into the pyrolysis oven. So you effectively have 7 opportunities to do this with MTBS-TFA and only 2 to do it with TMAH. And so I've been leading the TMAH experiment on SAM and trying extremely hard to select just the right sample to perform this experiment on Mars. And so that's what you're going to hear more about in just a moment here. Now, I keep talking about this reagent, TMAH, but I'm not really telling you why it's so useful. So unlike MTBS-TFA, this TMAH can release polar molecules. They're bound within macromolecules. So if you think about life as we know it, what this does is, if you do any kind of biology, microbiology, you may recognize the cellular membrane. So what you're able to do here is to liberate the fatty acids that are part of the phospholipid bilayer here, liberate them from the cellular membrane and make them detectable to GC MS. We can also perform a similar experiment, or you'll have a similar response with sort of the breakdown products from kerogen or insoluble organic matter from, for example, meteorites. So here's the way it actually works. And if this is too much to take in, what you want to be able to focus on is that in the white box here, if you have a fatty acid that you have liberated from that cellular membrane, if you just try to run it on the GC, you're not really going to be able to see it. Now, that's what that X is here. But if you react it with TMAH, if you rip that hydrogen off of that OH group there and add that methyl group, now you'll be able to see it in your chromatogram. So that's why it's so key. And so that's why we've been really interested in performing this experiment on Mars, because if there is, modern Martian life that has a similar biochemistry to terrestrial life, this should liberate fatty acids and other lipids from the cellular membrane and from the cell. Lipids can be preserved over extraordinarily long time periods in geologic samples. And so even if it's not these fatty acids, TMAH is a really powerful reagent for making volatile and liberating all kinds of molecules from macromolecules. And so that's why we wanted to perform this experiment. And that's why we wanted to be extremely selective in where we perform the experiment. So just to set the stage finally for performing this experiment, let me show you the organic matter that we've seen on the surface of Mars up to this point. So keep in mind, back in the 70s, we sent Viking to look for life on Mars. And Viking performed some experiments and said, actually, there's not really a reaction that makes us think that there's even organic matter on Mars at all. And it should be there. There should be organic matter from meteoritic infall, from interplanetary dust particles, but we're just not seeing it. And now, we have all of this detection from the SAM instrument, and we actually understand what went wonky with the Viking experiments. There's actually really powerful oxidizers on Mars that affected those experiments, and so that's why they weren't detecting organics at the time. Did I hear someone speak up? No.
I think you're good.
All right, thanks. Everyone's still awake, right? Life on Mars. We'll stay awake for that. Awesome, awesome. All right. So we have, just from the SAM instrument operating for 9 Earth years, we have this suite of organic molecules that we've detected on Mars. I mean, this is revolutionary for Mars science. We've been building up this story of organics that we can detect, why we think they're there. So many of them appear to be the breakdown products from, remember that word I said, kerogen. So this is some of that organic macromolecular material that's formed in meteorites. And so that material is deposited on Mars. It breaks down from radiation processes, from redox processes. And so you end up with these little fragments that we're able to see with the SAM instrument. And that's what I'm showing you here. All these ones in black have been detected with that evolved gas analysis, the EGA that I mentioned. Those in blue have also been detected in our GCMS analyses. And the ones in orange are what we are, what we have most recently been detecting just with the GCMS experiments. So all these sulfur-bearing organics, which it appears is related to the preservation of the organic matter when it's bound in with these sulfurs. So this is a recent science paper that came out in 2018 talking about the detection of thiophene and sulfur-bearing organics. And the paper that describes all of these new organics from our Glen Torridon region was just submitted to JGR Planets in the past couple of weeks. So all of that should be coming out in the near term. So finally, hopefully I've set so many stages here to tell you about our first TMAH experiment on Mars. So we were, when this experiment was performed, in the Glen Torridon region. This has been a really intriguing area since before we even landed on Mars, because we could tell that it had a lot of clay minerals. And on Earth, clay minerals are really great for binding organic matter to the mineral surface and helping to preserve it. So that's where we want to look for a lot of organics on Mars. So we actually performed the first of 2 TMAH experiments at the Mary Anning drill site in what we call the Knockfarrell Hill member. So we get to name all of this stuff informally on Mars so we can keep track of it. And all this was performed in fall of 2020. And so here's the target sort of in our larger scale image, orbital image. And so you can see the top pie graph here is showing you the mineralogic breakdown of the sample. A ton of clay minerals, and then some of the mafic minerals that we expect on a mostly basaltic planet, feldspars and pyroxenes, and then a little bit of salts, right? Calcium sulfates here. And then if you look at the bottom right image, this is, I mean, when you think about, you're drilling a hole on Mars, it's so extraordinary, and it really is. But these drill holes are about 6 centimeters deep. So it's an extraordinary process, and it's amazing we have the engineering to do it. When you think about the very limited amount of data that we still are able to collect from Mars, it's really mind-boggling. So here are the Mary Anning drill targets here. And so let me talk about our TMAH experiment. So it was successful. Otherwise, I would probably not be able to kind of sell this story quite as much. We were able to run basically a blank or a dry run using the same procedure and just not puncturing that cup and delivering sample to it. And that's what's in blue on this diagram. And then when we ran the experiment, you can see the black line is showing you basically all the ions we were able to detect in this combined EGA and GCMS experiment. So the experiment was successful. We see the byproduct from TMAH decomposition, which is trimethylamine, present at like 2 to 3 times the background levels in that blank. So the experiment certainly occurred. And we were able to detect a variety of organic molecules. And so let me share some of those data with you here. So this giant peak is actually just a background product of a little bit of MTBS TFA vapor that's been in the system since we landed. And so that's why this giant peak is here. And so what we're really looking for is the needle in the haystack, the very small peaks in this chromatogram. And so you can see kind of these little bumps along the chromatogram. These all correspond with different organic molecules. So we see, I don't have to go into detail on each of these molecules for you to be able to see that it's a bunch of aromatics, which means they're ring structures, and several that are like double ring structures. In this case, just the naphthalene, a double ring structure, and then some of those sulfur-bearing organics as well, like this benzothiophene. So this is just one of the GC columns we ran this experiment on. We're actually able to send the organics from the trap to 2 columns. So the second column is where we really get some interesting results. So here what you're seeing is a variety again of aromatics or ring structure organics. Some of them have double ring structures like this dihydronaphthalene, methylnaphthalene. Some of these are known background organics in SAM from reactions of that MTBS TFA with our hydrocarbon trap, with our injection trap material. So like this diphenylmethane way back here at the end of the run. But a bunch of these appear to be indigenous to Mars. And so the big question is, where are they from? And so one of the things that I've marked on this diagram, these stars are showing you TMAH reaction products with the Murchison meteorite. So Murchison is, I think, a CM2 meteorite, which means that it is the same kind of material that should be raining down on Mars and providing organics. And so what we want to understand is if you perform this experiment with the same kind of material that should be raining down organics on Mars, do you see the same products? And it looks like in so many cases, we do. And so it's starting to lean towards potentially a meteoritic origin for a lot of these organics. But I mean, they could also be geologic as well. So the big summary findings from our first TMAH experiment that we're still resolving some of these sources for, we're still working on the complete story of this, and we are hoping to get this submitted in the very near term. So this TMAH experiment was successful, and that's really important, not just for the second experiment on SAM, but TMAH is flying on the MOMA instrument, which has an acronym that at least describes what it does. It's the Mars Organic Molecule Analyzer on the European Space Agency's ExoMars rover. So we're flying this reagent again on another GCMS instrument in order to perform similar experiments to learn more about what might be preserved in macromolecular structures on Mars. So it's great the experiment worked. This sets us up for all future TMAH experiments. And then we detected these organic molecules. So the methylnaphthalene, the benzothiophene, these 2 top molecules here, it's going to be really hard to generate those from SAM internal sources. So we feel pretty confident those are indigenous to the sample. So are they meteoritic? Are they geologic? Some could argue like there might be a mechanism to make them biologically and see them, but I'm really going to lead you towards the meteoritic or the geologic sources for this one. We also see benzoic acid methyl ester, which is sort of the category of organics that we expected to see from this kind of reaction. So it's good to see it. We know there's benzoic acid that's generated on Mars as well as within the SAM system. And so we're trying to deconvolve which source it's coming from. Now, those fatty acids from cellular membranes, we did not detect them. We're still, searching for other methyl esters within the data. But our second TMAH experiment is working to be optimized so that we can do a better job of looking for fatty acids, which do exist in meteorites as well as being part of cellular membranes for terrestrial life. So this is sort of what's going on with all of our SAM and Curiosity work. We're moving forward on so many fronts there. And Curiosity is really a mature mission at this point. And so I'm going to wrap up this part of our mission arc and move into our Perseverance side of things, and show you some of the really rather recent stuff that we've been doing with Percy. So let me bounce over to, we're not moving too far away from Curiosity in the grand scheme of things. Mars is much smaller than Earth, but we're going to go over to talk about Perseverance here. So Perseverance landed on February 18th of this year. I've had the opportunity to join that mission as a participating scientist. And so I love this image. I wanted to share this with you all. This is not rendered on a computer, like made by an artist. This is what Mars looks like from one of our satellites. So this is the Jezero Delta that has, it looks like it's pouring in still from the crater rim into Jezero crater. And the image here, you I've got it zoomed in. This is actually Perseverance landing on Mars with the supersonic parachute deployed above it. It is coming into Jezero crater to land. So I think this is just an absolutely extraordinary image. So why did we go to Jezero crater with Perseverance? For a couple of reasons. So one is that, you know, right now, modern Mars is this really cold and dry desert. But 3.5 billion years ago, it had liquid water. We have extensive evidence for liquid water. One of the other reasons is that the oldest rocks, or more than 50% of Mars's surface, is composed of these really ancient rocks, more than 3.5 billion years old. Such rocks on Earth are extremely rare. And I've got a map here showing just a few examples of where some of these cratons are and where some of these really ancient rocks can be found. So Mars is giving us this unique window into what a habitable planet would have looked like in its infancy. So we have sort of the habitable environment preserved over extraordinary long geologic timescales. And that's another reason that we go to Mars to answer this question, and that we went to the Jezero region specifically. Now, when I talk about the Jezero Delta and the Delta environments, one of the things we're interested, of course, in looking for are biosignatures. So what biosignatures should we look for? And I think, you know, talking about microbial communities so much, you know where this is going. So the classic fossils that so many folks think of who don't necessarily do geology or who focus more on macro scale paleontology are all, you know, younger than 650 million years old, which is old, but not geologic time old. And so what do we really want to look for on Mars? So microbial biosignatures, so basically bacteria and archaea generate at times these macro scale structures, these stromatolites, but they can also, as we've talked about at the beginning of this presentation, leave behind evidence for themselves in their stable isotopes, in organic molecules, in chemical trends along strike in a lacustrine environment, all kinds of great things. So this example on the right is showing, you know, an ancient stromatolite, microbial biosignature. And these are connected to modern microbial mats that we see forming on Earth today. I've got these really gorgeous examples of these underwater microbialites from ice-covered lakes in Antarctica, which are some of our last remaining examples of basically stromatolites growing in the modern. So it's these kinds of structures and communities that we're searching for when we say we want to look for ancient life on Mars. So this is what we're looking for. This is why we go to Mars. But I have to say that seeing us land on Mars is more breathtaking than the greatest stromatolite I've ever seen. And here we go. So you should be able to see a couple of different videos playing at the same time here. So this is a combination of different cameras looking at our landing process with Perseverance. So we use the same sky crane maneuver to land Perseverance in Jezero that we used to land Curiosity in Gale Crater. So the image on the left here is showing you our supersonic parachute that's slowing us down as we enter the Martian atmosphere. The image in the center here is showing a camera looking up from the rover deck up at the sky crane as it is dropping the rover down on this tether. And then lastly, on the top right, you're seeing the rover approaching the ground surface to land. So what happens after we all 6 wheels touch down is that tether is released, and Sky Crane flies off to go crash land somewhere else and not on top of the rover. Remember that when we did this with Curiosity, we hadn't tested this end to end before. And so we were all like, is this thing gonna work? And it absolutely did. So at least we had the confidence. We've seen it work once before, having it do this again with Perseverance. So these videos are simply spectacular. We did not have these for Curiosity when we landed in 2012. And now I just want to put up this still image for a moment. I think this is one of the most extraordinary images from planetary science, on par with Apollo mission level images. Us landing another vehicle on another world, being able to document it effectively with GoPro technology. These were add-ons sort of at the last minute, but just seeing this incredible engineering come together to deliver this incredibly advanced scientific suite to Mars to address these questions. Okay, so we've got Perseverance on the ground. Let's talk about what we're doing in Jezero. So this is, instead of a perspective image, sort of just a aerial image of Jezero crater. You can see the main trunk of the river that would have poured into the lake, and then your delta deposit as those sediments slow down as they're depositing into a lake environment. So without a question, this deposited in a lake in ancient times, ancient geologic time on Mars. And so the image on the right is showing where we landed with Perseverance, and this potential traverse path actually doesn't mean anything because we got really interested in what was going on sort of down under this sort of thumb of this etched lower airfall deposit. And so we're actually down here sort of where the W is on lower, exploring this really interesting crater floor unit before coming back out, going around that etched airfall deposit and then moving towards the delta. So why do we want to explore a delta in the first place? River deltas are really habitable environments on Earth. We know that they had to be deposited by water. We know water was present. And so this is one of the reasons that we would want to go to Jezero crater to collect samples that have the potential to preserve biosignatures. And so I have to put in this plug. Our first science paper from the mission came out maybe a month ago, documenting this absolutely fantastic delta remnant here that we named Kodiak. And so you can see the 4 sets, bottom sets, like you can see the delta structure preserved in this little remnant that's about 1 kilometer away from the major delta front. And so we were able to, we documented the layers in this delta front, as well as these long distance images we were able to take of, so we documented these layers in Kodiak and then also the delta front, and saw some of these massive boulders that we know had to be deposited by episodic flooding. So these are just some of the sort of teasers that we have as we're waiting to go explore the delta itself. We can see all of this really extraordinary geology just waiting for us. So I keep talking about collecting samples, and I want to bring your attention to sort of a larger scale of the Perseverance mission. So unlike Curiosity, which is taking samples and analyzing them in situ, while Perseverance can do that in part of the mission is also to sample and cache the samples for eventual return to Earth as part of the Mars sample return architecture. I would say this is the grandest architecture since the Apollo era. This is a massive undertaking to collect samples, and this would be the first time that we've brought samples back from Mars ever. So the only samples of Mars that we have right now are Martian meteorites. And so, this diagram we've had since before landing, describing how we're going to collect and cache samples for return. But I've got these images of actual core samples that we've collected with perseverance. So on the sort of middle right here, this is our most recent core from, I think, Monday. This is the target Select that we have cached away in our little sample tubes. The diagram on, or the GIF on the left here is showing you what's going on with the, let's see, Sol 262. Okay, so this one is also from Select, showing you the core in the sampling tube, and then we perform these volume measurements to basically see how much of the core is present in the tube, and then we seal it so that it is hopefully safely preserved for the time it needs to wait on Mars for us to be able to collect it. And we have the video that I'm showing here. The GIF is this cache cam, so basically our camera that allows us to take an image inside of the caching tube and confirm there's a core in there. Now I've got a QR code up here, and so I'd encourage you, you can get your phone out, just turn on the camera and hold it up, and it will link you to Sketchfab, which will enable you to look at a bunch of 3D renderings. I want to see like everybody's like phones up against their cameras here, but I don't see it. That's okay. It lets you see the 3D renderings of a bunch of our targets that we've explored on Mars so far. And so the image down here is showing one of our outcrops. I believe that this is Rochette. The rock is Rochette, and the paired cores that we have here are Montdenier and Montignac. And so we have basically two samples from this outcrop, one of which is slated to be returned to Earth. And so just to give you our final sort of closing story about Mars sample return and the exploration of Mars here, this is a notional 3-mission process. So we are here with sample collection with Perseverance. There's Percy looking down at our helicopter, Ingenuity, or Jenny. So collecting these samples and then putting them into 2 caches or places where a future mission will pick them up. Our second step is both the Fetch rover, which is being built by the European Space Agency, and the Mars Ascent Vehicle, or the MAV, which is being built by NASA. The Fetch rover is going to grab the cache, take it over to the MAV. I'm going to put it into a secondary cache, and then we're going to launch a rocket off the surface of Mars and send these samples into orbit, where our third mission is going to be orbiting, waiting to collect those samples, grab them, and bring them back to Earth. So you can only imagine, you know, I've shown you these images of Mars. I've shown you the chemistry and the organic work that we can do, the elemental analyses we can do with all of these instruments on board the rovers. It's absolutely revolutionary, and it's also so limiting. There's only so much you can do. If I want to see a rock, we have to ask the rover to turn and take a picture of the rock. There's only so much you can do with the robotic interface. And so having these samples, as small as they are, they're incredibly precious, and they are going to truly revolutionize our understanding of Mars moving into the next several decades. So Mars sample return is something to keep your eye on. It's going to be absolutely extraordinary, not just for Mars science, but for planetary science as a whole. So with that, I'm going to leave you with our evolution of rovers on Mars, leading up to Perseverance and Ingenuity. I want to thank you so much for your time, and it looks like we have time to take questions. So thank you.
I have a question.
Please.
So I'm just curious, when you're looking at the GCMS results, how do they compare, say, with modern or with ancient microbialites on Earth? You know, what would an Earth microbialite look like in terms of those same biosignatures?
Oh, looking for the biosignatures.
Mm-hmm.
So oftentimes what we would do with more ancient samples, or we need to look for the most recalcitrant molecules. And so this leads us down the path of like hopanoids or hopanes. So these larger structures that are able to stick around over the billions of year time scale, as opposed to, I think the oldest fatty acids that we've been able to detect are on the order of just a couple million years old. So to identify like a hopane or a hopanoid, we wouldn't be able to do it with the SAM instrument as it's on Mars today. And so that kind of constraint is actually driving a lot of instrument design today for future missions. So instruments that are built to effectively do, blind dye or solvent extraction on Mars, like that's sort of the gold standard, right, for terrestrial labs. So I'm working with 2 different projects that are trying to develop ways to build those kinds of front end sort of extraction devices so that we could get at those more complex and origin diagnostic molecules. Yeah.
What I think I'm asking is, what would, if you ran the same SAM experiment on a microbialite on Earth,
Mm-hmm.
what would the data look like compared to the Martian data?
I think that you would probably see a lot more, depending on the age of the microbialite. You may be able to see fatty acids. You could see decarboxylated fatty acids in the form of alkanes. You might be able to see some of the shorter chain like alcohols. I think that you would see a lot of sort of smaller breakdown products. And then as you get older and older in geologic time, you're going to have more and more degradation.
That's what I was saying, like if it was like in a Proterozoic stromatolite, how similar would the Martian signature look to, really like a Proterozoic?
Yeah. And so that's where I'm thinking like only those most recalcitrant molecules are going to stick around. And so I think if you do a TMAH experiment, so actually we are doing this with like 2.5 GA BIFs from South Africa. And you really see just a couple of aromatics. Benzene is like always around. And so in that case, it is very similar to what we see with the TMAH experiment on Mars. But on Earth, it's always so hard to deconvolve both the ancient and any modern incursion of microbial input. And so that's where the challenge really lies in doing that kind of direct comparison. But I can say like TMAH experiments with like very carefully handled, 2.5 billion year old samples, they're very lean using SAM-like techniques, which is sort of what you anticipate.
Thank you.
Yeah, that's a great question. Thank you.
Before we open up the whole floor for questions, I will say we'd like to open it first to any students. If any other students have questions, and then after students have asked, we can open up to everybody.
And feel free to write in the chat if you prefer instead of speaking up. Totally fine with that as well. I see some people went to the Sketchfab and were able to poke around on there. So there should be other images, not just of Rochette, that you're able to 3D manipulate there, which is it's just fabulous.
And if no students have questions, we can open up. It sounds like no students are asking, so we can open up back to everybody. Sorry, Tom. We have one from Ben.
Great.
Hey, great talk. I'm just curious about the gas chromatography on the SAM suite. You mentioned that there are a certain number of cups you can possibly use to analyze samples. I'm wondering if the helium used to pump the gas chromatography is also a limiting factor, or if that gas is ultimately recoverable and reusable.
It is a limited resource, absolutely. Yeah, and so we have, you saw in the carousel, there's sort of 2 tracks. So there's actually, everything is done in at least duplicate, just in case something goes wrong. We have like 2 brains in the computer on the rover as well. And so there's actually 2 separate helium tanks that run on the 2 separate carousels that function with 2 separate pyrolysis ovens. So the whole thing is meant to have enough redundancy that we can perform experiments on one side, even if the other side fails. For the wet chemistry side, all of those cups are on the same carousel ring. So we are being careful to ensure we have enough of those consumables for the rest of our wet chemistry experiments. So, I mean, yeah, it's a limited resource, and eventually, you know, both of these rovers are powered with RTGs. So they will eventually run out of enough power to run these really energy intensive experiments. But I mean, it's quite a ways down the road. They're really robust power systems.
Awesome. Thank you.
Yeah, that's a great question. A lot of people don't even think about like all those other consumables that go into this. I do see a question in the chat. I don't know if someone else wanted to moderate, but when will the samples get back to Earth? So Mars sample return is nominally scheduled to bring samples back in the early 2030s. So it's a 10-year ordeal. We're collecting samples. We have to deliver our first cache in the next couple of years by the end of the prime mission of Perseverance, but we'll be able to keep going after that, exploring Jezero and outside of Jezero. And I think we're going to launch, I think our next 2 launch windows for kind of step 2 and 3 of Mars sample return are in 26 and or 28. Like those are 2 good launch windows for sending those other 2 missions that would bring the samples back. Great question.
Oh, we have another question in the chat. Tom asks, what is the range of rock types detected by the rovers outside of the igneous suite, and are there carbonates?
So which mission? So I can say that we
Either one.
Okay, yes.
All
So
of them.
all of them. We've seen carbonates with gosh, Valerie, you probably would remember, not Spirit. Was it Opportunity? Where was Comanche? I can't remember.
The Spirit rover detected some carbonates in the like Columbia Hills region of Gusev Crater.
Yep. And then we are arguing about the detection of carbonates with Perseverance. There's definitely carbonates from orbit that we see sort of in the bathtub ring around Jezero that are associated with olivine bearing strata as well. So that's part of what we're trying to explore with Perseverance now. And then, I mean, yeah, like, so Gale Crater is this, sedimentary, wonderland, right? Like we're in this like lacustrine system, fluvial lacustrine system. We have these like gorgeous aeolian deposits. And we're just now getting into the sulfate bearing unit. And so it seems to be a lot of like calcium sulfates, gypsum, basanite, and hydrite in Gale as we're sort of moving up from the clay bearing unit of Glentoridon that I talked about, kind of moving up the mountain. So we're starting to see sort of new mineralogy, but a lot of the sedimentology is very familiar. Whereas with Perseverance, we see the delta, we know it's a delta structure made by water from a river flowing into a lake. But we are discussing these really intriguing mineralogies and textures that we're seeing in the crater floor that we're currently exploring with Perseverance and trying to understand, is this a lake bottom? Is it, an igneous relic of the impact? Are there lava flows? So we're still getting our bearings with Perseverance. And you can imagine doing this remotely. It takes a lot more time than if you could just stomp around on the outcrop for a while.
Hema has a question in the chat. Out of curiosity, I don't know if that was a pun.
I hope so.
What is the stratigraphic context in the block drilled on Monday? Also, where within stratigraphy, pore set or bottom set, etc., do you expect to see organic material that you found in part 1?
All right, excellent. So we are trying to understand whether there is stratigraphic context for the rocks that we've been most recently drilling. So I should say we are trying to understand that context as we are collecting samples, but part of the design of the return sample side of things is that we want to collect samples from the oldest units that we're going to be able to explore. And so the crater floor there is likely to be it until we climb out of the crater and get up onto the rim. And so we are actively determining context as we're collecting these samples. And we're on such a tight timeline to meet Mars sample return deadlines that it all is sort of happening together as opposed to like context. Okay, let's sample here, context. All right, let's sample this next one. We just don't have that time for this particular mission. And then where in the stratigraphy do you expect to see organics? Excellent question. That, again, something that the organics folks on the mission are arguing about in like exactly where we should go. So the terrestrial canon suggests that bottom sets, the finest grained materials, the lake deposits, distal lake deposits should be good places to look for organics that are absorbed to those clays. The story is evolving as we're trying to understand what the crater floor material actually is. But once we start going toward the delta bottom sets that are still exposed from that eroded delta front, those are going to be environments where we're going to be looking for organics, both with our Sherlock instrument, which is a deep UV Raman instrument, as well as collecting samples for return, where we're really hoping to have preserved biosignatures in these environments where if they are present, if they were ever present on Mars, this is where they should be. And I see another one from Tom here.
Yep, there's another one. So what are the odds of actually seeing a good microbial texture that we'd all agree on? Or is there a geochemical signature that would convince you?
So I keep saying in all of these talks that we will never agree until we bring a sample back to Earth and do everything we can do to that sample to convince ourselves. And even then there's going to be holdouts. It's one of those extraordinary claims require extraordinary evidence. And I think that sample return is the only way for us to feel completely confident in a finding based on just the experience I've had working on 2 missions where, if there were dynamic macrofauna, we would have met it already, or we would have, seen it preserved in the rock record already. I feel like if it was really abundant. And so that's where we're really looking for that needle in a haystack. A geochemical signature that would convince me, yes, if we ran that Tmah experiment and we saw a distinct, even over odd preference for fatty acids, that is a fingerprint for life on Earth. And even if it were odd over even preference, anything like that suggests a process that is selecting a certain chain length, or if you're looking at handedness of amino acids, if you see a preference for left over right-handedness, all of that can indicate biosynthesis processes that would be incredibly compelling. And that's what I keep hoping to find one of these days with TMAH.
That actually brings up my own question. I know that it seems that this talk was very easy for me to follow, even though I don't do any of this. So it seems like you definitely have an aspect of interest in scientific communication of some kind. And I'm wondering, with the general public, how do you compel them to think about this stuff as life, I guess, when it's at that small scale? And even for people in the sciences don't necessarily look at that stuff as life either. Like, how do you do that, or how do you think we should do that?
Yeah, when I do outreach talks for general public audiences, a lot of the times people often ask me well, why, other than the neat factor, why should I care? Which as a scientist, I'm always like, it's so amazing. Look at all of this. We're learning about comparative planetology. You're understanding the evolution of the rocky planets in the inner solar system. You're looking at the history of life on Earth and whether life could arise other places. I mean, there's so many fundamental questions that can be addressed with this kind of work. So I often remind folks that, without the Apollo Mercury programs, basically the whole start of the space program, you wouldn't have Velcro, for example. So the need to innovate to accomplish this science on a small scale, on a higher level, has really motivated us to push ourselves, to develop new technologies, to develop new techniques, to be able to accomplish this science. And so when people ask like, well, what does this really do for me? You know, I think about like all of the innovation that has to happen to support this exploration actually does feed back into the things that we use as people on an everyday sort of cadence. But I when I do like interviews and stuff like that, you know, I try to also remind people of the more profound side of things, that, you know, it's just us, it seems like an awfully big waste of space, which is what Carl Sagan, you know, his famous quote is. And that really motivates me as an astrobiologist. You know, even if you think there's life beyond Earth, if you're looking for that evidence, as I am, with, again, that a priori assumption that maybe it is just us, you know, that gives me a far more, I feel like a deeper sense of the rarity of life, the preciousness of it. It leads me back into conservation and being a responsible steward of the environment, the whole 9 yards, right? So like, it really gets into this deep realm of all of this actually does impact like the way you think about things, as well as the way you get to, you know, use tools in your day-to-day life.
That's great. You should have a podcast. We have one more. I think we're going to end on this question from Luke in the chat. For future use, how do you plan on releasing the results to the public once the samples have been analyzed, if possible?
Awesome question. So all data from all NASA missions is posted on the PDS, which is the planet. Valerie, what is it? Planetary Data System?
Something like that.
Something like that. So all data is available roughly 3 months after we collect it. And the embargo is just meant to enable those of us who work on the mission to also get to do our science in addition to doing, you know, daily rover operations. And then of course we publish our findings, and we're working really hard to publish complete data sets in the SI supplemental material so that others can perform these experiments. They can, you know, the analog experiments, they can follow up on all of this. Oh, excellent. Thank you, Francesca. That's perfect. So yeah, we share that information as rapidly as we can with that minor embargo, just to make sure we're able to get some of our science done. And in fact, I'm on Perseverance rover ops tomorrow, which is like such an honor and also such a time sink. But yeah, it's out there for everybody to access.
Well, great. Thank you so much, Amy. And also thank you, Sydney, for the great introduction. I think we'll end it there. And yeah, thank you again for coming. And we hope you have a good rest of your evening down in Florida. And
thank you so much.
Yep. Have a good one.
Awesome. It was great to meet everyone. Thank you so much.
Thanks a lot.
Nice talking, Amy.
Stop the recording.
Thank you. Thanks, Sydney.